Hi, I'm Mark Barsamian. In this video, I'll be discussing Euler circuits, Euler trails, and Hamiltonian circuits. This material is from Chapter 10, Theory of Graphs and Trees, Section 10.1, Trails, Paths, and Circuits. This is actually the second video on that section. The corresponding reading is pages 684 to 692 of that section, examples 6 through 10 of that section. The corresponding homework is this collection of 8 exercises from section 10.1. As I said, I'll be discussing Euler circuits, Euler trails, and Hamiltonian circuits. Recall the terminology of walks, trails, paths, closed walks, circuits, and simple circuits from section 10.1. These definitions of walks, and trails, paths, closed walks, circuits, and simple circuits are maybe best kept straight by making a table that summarizes their properties. So a walk can have repeated edges, can have repeated vertices, can start and end at the same vertex, doesn't have to. It does not have to even contain any edges. A trail is not allowed to have any repeated edges. That's the big difference between a trail and a walk. A path is also not allowed to have any repeated vertices and cannot start and end at the same vertex because, again, that would be a repeated vertex. So the difference between a path and a trail is no repeated vertices, including not being allowed to start and end at the same vertex. Now, a closed walk is a modification of a walk. That is, repeated edges are allowed in a closed walk and in a walk. Repeated vertices are allowed in a closed walk and a walk. The difference is a closed walk is required to start and end at the same vertex, whereas with a regular walk, it's just simply allowed. So every closed walk is a walk, but not the converse. There are walks that are not closed walks. And closed walks, like regular walks, don't have to contain any edges. A circuit is best understood as being a modification of the idea of a closed walk. That is, it has to start and stop at the same vertex, like a closed walk, and repeated vertices are allowed. But the modification is that repeated edges are not allowed, whereas they are allowed with closed walks. And another modification is that a circuit must contain at least one edge, whereas a closed walk does not have to contain any edges. A simple circuit is best understood as a modification of the idea of circuit. So, like a regular circuit, repeated edges are not allowed. It must start and stop at the same vertex, must contain at least one edge. The difference is that while a regular circuit allows a number of different repeated vertices, for a simple circuit, only the first and last vertex can be repeated. So in other words, a simple circuit starts and ends at the same vertex. That's the only vertex that a simple circuit visits twice. Now we have a new definition, what's called an Euler circuit. An Euler circuit is a circuit that contains every vertex and also contains every edge. So let's add Euler circuit to our table of other kinds of walks. It's most useful to compare it to the other kinds of walks that must start and end at the same vertex. So those are the closed walks, the circuits, the simple circuits, and the Euler circuits. Well, as the name implies, an Euler circuit is a circuit. So repeated edges are not allowed, and repeated vertices are allowed. And it must start and stop at the same vertex, and must contain at least one edge. But the difference is an Euler circuit must use every edge, whereas a general circuit does not have to. And an Euler circuit must use every vertex, and a general circuit does not have to. An important thing to note is that a closed walk can have no edges and can have repeated edges, whereas all the kinds of circuits must contain at least one edge and cannot have repeated edges. Example 1. For the given graph, draw a walk of the indicated type. Well, let's start with a closed walk. Let's go recall the definition of closed walk, or the properties of closed walks. They have to start and end at the same vertex. They don't have to contain any edges. They can have repeated edges. They can have repeated vertices. But they don't have to use all the vertices. They don't have to use all the edges. So my closed walk is going to be this. That's my sequence of vertices. Notice that I don't have to label the names of the edges in order for that sequence to fully describe the walk. There's no ambiguity in what that's describing. But it is hard to draw. Notice that drawing the walk, I actually had to veer off of that actual edge. That almost looks like I've got a graph that has 5 edges connecting vertex 1 and vertex 2. The graph doesn't. The graph has just one edge. It's just that that edge has gotten used 4 times. So that's a closed walk. Now what about a circuit? Let's go back up and review the definition of circuit. A circuit has to start and end at the same vertex, has to contain at least one edge. Repeated edges are not allowed. Repeated vertices, however, are allowed. Well, here's the circuit that I'm going to draw. Now there is kind of a sloppy description of this circuit because there's some ambiguity here. I go from vertex 5 to vertex 1 and back to vertex 5, and it's not really clear how I do it. So I should actually be more precise. I really need to label some edges here. I need to have those edges labeled in order to make this a precise description. So with those edges labeled, I can now make a more precise description of my circuit. There's my circuit. I can highlight it in blue, and I can add arrows to indicate the direction of travel and the start and end point. Now, simple circuit. What's up with that? Simple circuit is similar to a circuit except that the only allowed repeated vertex is the first and last one. So a good simple circuit would be this one. Now finally, an Euler circuit. Let's go back up and see what an Euler circuit has to be. An Euler circuit has to start and stop at the same vertex, has to contain at least one edge, must use every edge, but cannot repeat any edges, has to use every vertex, but vertexes can be repeated. Well, here's my Euler circuit. Now I can highlight this, but of course every edge has to be used, and so it'll end up looking kind of silly because of that. So I'm going to just list the vertices. Now we saw before that it's helpful to have those 2 edges named, edge 1 and edge 2. So here's my Euler circuit. Here's my Euler circuit. I can try to draw it. I'm going to draw it by fudging a little bit so that my lines don't cross. So there you see those edges actually touch V2, but I've drawn the path in a way that it looks like they don't. But vertex 2 gets visited twice. It gets visited on the way through the first time, and then on the way through later. Let's go on. Let's notice this one thing. If a variety of walk has a requirement that repeated edges are not allowed, then any vertex that has an odd degree must either be the start point or the end point of the walk. That's an exclusive OR. That is, the vertex cannot be both the start point and the end point. Let me draw what I'm talking about. So there's a vertex that has an odd degree. Now, if I have to use all those edges, and that means that I'm going to come into this vertex on one of those edges and then leave on one of those edges, like maybe that edge. And then sometime later, I'm going to come back in, and then I'm going to have to end at that vertex because I can't reuse any of those edges. Or maybe I started at that vertex and I'm leaving and coming back later. So you see that that vertex V, which has odd degree, has to either be the end point of the walk or the starting point of the walk. So I guess the observation should say, if the variety of walk has a requirement that repeated edges are not allowed, and also that every edge has to be used. If every edge doesn't have to be used, then maybe vertex V wouldn't get visited at all. So that brings us to this theorem. If a graph has an Euler circuit, then every vertex of the graph has to have a positive even degree. Let's think about why that's true. Let's go back. If there's a vertex that has odd degree, then that vertex has to be the end point or the start point, but not both. So it's impossible for the walk to be a circuit, because a circuit has to start and stop at the same vertex. Now, there's a contrapositive version of this. If some vertex of the graph has an odd degree, then the graph does not have an Euler circuit. So, for example, do these graphs have an Euler circuit? Graph G is a connected graph with 7 vertices of these degrees. Well, we see that there are 2 vertices that have odd degree. Theorem says if some vertex of the graph has an odd degree, then the graph does not have an Euler circuit. So the answer is G does not have an Euler circuit because it has a vertex with odd degree. Question B. Suppose G is a graph with 4 vertices, each of degree 2. Does the graph have an Euler circuit? Well, it might seem like the answer is yes. Seems like the answer to question B is yes. But wait a second. We don't know that graph G has to look like that. Graph G could look like this. This graph has no Euler circuits. So the answer to question B is not necessarily, or not enough information. Question C is, does this graph G have an Euler circuit? Well, let's make a note of the degrees. I'll label the degrees in red. We see that there are 2 vertices that have odd degree. Since there's a vertex that has odd degree, there's no Euler circuit. Let's go on. What if a graph does not flunk the 2 obvious requirements? That is, what if the graph is connected and has all vertices of positive even degree? Is that enough to guarantee that the graph will have an Euler circuit? That's the subject of this theorem. If a graph G is connected, and if every vertex has positive even degree, then G has an Euler circuit. Let's go back up and look at the previous page. Notice the problem with this graph is that even though every vertex has positive even degree, the graph is not connected. So we could not have an Euler circuit in that graph. This graph has every vertex with positive even degree, and the graph is connected. It does have an Euler circuit. So for example, suppose it's known that a graph G has 10 vertices with degrees 2, 2, and then all the remaining 8 vertices have degree 4, and that it's known that the graph G is connected. Does the graph have an Euler circuit? Well, yes, theorem 10.1.3 says so, but we should be very clear in our explanation. We should say something like this. So notice that my explanation uses theorem 10.1.3. If you look at theorem 10.1.3, it has some hypotheses. A graph G is connected, and every vertex of G has positive even degree. The theorem tells us that if those things are satisfied, then G has an Euler circuit. So you get to use the punchline only after you've confirmed that all the hypotheses are met. So my explanation started by confirming that the hypotheses are satisfied. I just said G is connected, and I said every vertex of G has a positive even degree, and then I just get to say the punchline then. Therefore, G has an Euler circuit. So that's how you use a theorem. That is, using a theorem doesn't just mean that you get to say the conclusion of the theorem. Using a theorem involves confirming that all the hypotheses are met, and then getting to state the conclusion. Let's go on. The proof of this theorem is in the form of an algorithm for constructing an Euler circuit for a graph G in which the degree of every vertex is a positive even integer, and I should say a connected graph G. The algorithm is shown on the next page. So there's the algorithm. Rather than go through all these steps, I think that I will do an example. Example 4 says, show how the algorithm works to construct an Euler graph for graph G shown. Well, let's go up and see what the algorithm tells us to do. Step 1, pick any vertex V of G at which to start. Well, let's let our vertex V be V1. What's next? Step 2 is to identify a circuit that starts and ends at V. Well, our circuit could be the following. What's next? Step 3. Check to see whether C contains every edge and every vertex of G. If so, then C is an Euler circuit, and we're done. But if not, we've got some work to do. So let's go back and check. So we should observe that C does not contain all the edges and vertices of G. So C is not an Euler circuit. All right, so then we've got more work to do. Let's see what it is. Step 3a says remove all the edges of C from G, and also any vertices that become isolated when the edges of C are removed. That'll leave us with a subgraph. We'll call that subgraph G prime. Well, the edges that I'm going to remove are all the edges of circuit C. So I'm going to remove those edges, and then any vertices that become isolated when I remove those edges, well, that'll be that vertex. So I need to remove those 3 edges and that one vertex from the graph of G, and then call the new graph G prime. All right, what's next? Step 3b is to pick any vertex W that's common to C and G prime. Well, notice that this vertex is common to C and G prime. So let's let that vertex be W. All right, what's next? We're supposed to identify a circuit that starts and ends at W and never repeats an edge, and call that circuit C prime. So we have to identify a circuit called C prime. Well, that circuit can really only be one of two things. We can either go clockwise or counterclockwise around that subgraph. Now what? Step 3D is to patch C and C prime together to create a new circuit as follows. We start at V and follow circuit C all the way to W, and then follow C prime all the way back to W. After that, continue along the traveled portion of C to return to V. Now, I can draw that, but I can also use the sequences of characters. So our job is to create this circuit C double prime. Now what we're supposed to do is we're supposed to start at V and follow circuit C to begin with. So there's circuit C, and we're supposed to follow that beginning with V. So we started with V, which is vertex V1, and we followed that red circuit until we got to vertex V2. Now that vertex is also known as W. Now what we're supposed to do is hop on to the other circuit, this black circuit from now on, until I get back to W. And then hop back on to the red circuit and follow the red circuit the rest of the way until I get back to V. The way that circuit looks is this. Something like that. Let's go on. Once we've finished these steps, we go back up to the start of step 3 again. We check to see whether our new circuit contains every edge and vertex of G. So we're doing step 3 again now. Well, when we get back to step 3, we observe that circuit C double prime contains every edge and every vertex of G. So C double prime is an Euler circuit, so we're done. That's how the algorithm works. So, as I said, this theorem is proved by this algorithm. We showed how the algorithm works in a particular example, but in fact, this is a general algorithm and it will always work. Let's go on. Now I want to talk about Euler trails. An Euler trail is a trail that starts at a vertex V and ends at a different vertex W. And it passes through every vertex of G at least once and uses every edge exactly once. So let's put that into the context of the other kinds of walks that we have that start and end at different vertices. So a walk doesn't necessarily have to start and end at different vertices. It can, doesn't have to, but the basic walk could be a walk that starts and ends at distinct vertices. Now the same thing goes for a trail. A trail can start and end at the same vertex, but it could start and end at different vertices. But with trails, repeated edges are not allowed. That's a difference between a trail and a walk. But trails don't have to use every vertex, and neither do walks. And trails don't have to use every edge. Repeated vertices are allowed in walks and trails. But walks and trails don't have to have any edges at all. Now let's consider Euler trails. Euler trails cannot start and end at the same vertex, and they have to contain at least one edge, obviously, because they don't start and stop at the same vertex. So that's a difference between a trail and an Euler trail. Euler trails have to start and stop at different vertices. Repeated vertices are allowed for both trails and Euler trails, but Euler trails must use every vertex, whereas a regular trail does not have to. And Euler trails must use every edge, whereas a regular trail doesn't have to. Now let's contrast an Euler trail to a path. They both have to start and end at different vertices, so they cannot start and end at the same vertex. A path doesn't have to have any edges, but an Euler trail has to. A path cannot have any repeated vertices, but an Euler trail can have repeated vertices. A path does not have to use every vertex, but an Euler trail does. And a path does not have to use every edge, but an Euler trail does. There is a useful criterion for knowing when a graph does or does not have an Euler trail. It's this corollary. If G is a graph and V and W are two distinct vertices of G, then there is an Euler trail from V to W if and only if G is connected, V and W have odd degree, and all other vertices of G have positive even degree. So for example, example 5, consider this graph. Does this graph have an Euler trail? If so, describe one, and if not, explain why not. Well, let's go back up and look at that criterion, that corollary. The only situation where you'll have an Euler trail is if you have two vertices that have odd degree and all the other vertices have positive even degree. So let's look at our graph and consider the vertices and their degrees. Now we've examined this exact graph before. There are the degrees of the vertices. Vertex 2 has degree 5, and vertex 5 has degree 3, and those are odd numbers, and all the other vertices have even degree. So yes, it has an Euler trail, so it must start and stop at one of those odd degree vertices. So let's just describe an Euler trail. Let's put some edges in to help us describe the trail more precisely. Notice that I've described that trail just by giving vertices with one exception. I had to describe what's going on when I go from vertex 5 to vertex 1 and back to vertex 5. I had to list the edges. But look at this. I have V2, V2. Well, the only way that that can happen is if you go around this loop. So listing V2, V2 is enough. Also notice I list V3, V3. That can only happen by going around that loop. Notice that this trail starts at V5. That's one of the odd numbered vertices, and it ends at V2, which is one of the odd degree vertices as well. Question B, does this graph have an Euler trail? Well, let's look at the criterion. The criterion is this. We have to have two vertices that have odd degree, and all other vertices have to have positive even degree. Well, we've seen this graph before. Remember that this graph is notable because all of its vertices have degree 3. So the answer to the question is that this graph does not have an Euler trail because there are too many vertices with odd degree. Let's go on. Hamiltonian circuits is the next topic. A Hamiltonian circuit is a simple circuit that includes every vertex. That is, a Hamiltonian circuit is a sequence of adjacent vertices and edges in which every vertex appears exactly once, except for the first and the last, which are the same. A remark is in order. Note that although an Euler circuit for a graph must include every vertex of G, it may visit some vertices more than once, and hence it might not be a Hamiltonian circuit. On the other hand, a Hamiltonian circuit does not need to include all the edges of G, and so a Hamiltonian circuit might not be an Euler circuit. Let's add Hamiltonian circuit to our table of the kinds of walks that we've learned about that must start and stop at the same vertex. In particular, let's compare Hamiltonian circuits to Euler circuits. Let's highlight the differences and the similarities. Euler circuits have to use every edge, whereas Hamiltonian circuits do not. Euler circuits allow repeated vertices, whereas Hamiltonian circuits only allow the first and last vertex to be repeated. Otherwise, they're similar. Repeated edges are not allowed, and every vertex must be used. They must start and stop at the same vertex, and they must contain at least one edge. An important thing to remember is that a closed walk allows repeated edges, whereas all the various kinds of circuits do not allow repeated edges. There's a useful list of properties of graphs that have Hamiltonian circuits. It's articulated in this proposition. If graph G has a Hamiltonian circuit, then G has a subgraph H with these properties. H contains every vertex, H is connected, H has the same number of edges as vertices, and every vertex of H has degree 2. Example 6a. Does this graph have a Hamiltonian circuit? If so, describe one. If not, explain why not. Well, this graph does have a Hamiltonian circuit. I'm going to highlight it. Notice that that's a subgraph that contains every vertex, is connected, has the same number of edges as vertices, and every vertex has degree 2. Question B. Does this graph have a Hamiltonian circuit? If so, describe one, and if not, explain why not. Well, this graph does not have a Hamiltonian circuit. Now we've got to explain why not. Well, the idea is this. Let's consider what goes on at vertex 7. There's got to be a subgraph that includes vertex 7, and vertex 7 has to have degree 2 in that subgraph. That means that I've got to get rid of 2 of the edges that touch vertex 7. But if I get rid of these 2 edges, then that's going to mean that the graph is not connected. If I get rid of these 2 edges, then that's going to mean that vertex 2 and vertex 3 won't have degree 2, and so forth. We can write this down. So again, if vertex V7 is part of a subgraph H in which its degree is 2, then 2 of these green edges are going to have to be removed and not included in H. That'll result in H either not being connected or in 2 vertices of H not having degree 2. That's the end of that example, and that's the end of the video. Thank you.